from two populations and introduction. You've seen how to carry out a hypothesis test for a single population proportion. With very few changes, this procedure can be altered to accommodate a more interesting situation, comparing proportions from two populations. So we'll be looking at scenarios where we have two population proportions, and then we're going to try to decide if they are different or the same, and like what's the likelihood that they're different or that they're the same, using hypothesis testing, but like a slightly different variation of hypothesis testing that you saw before because we have a different situation. Let's look at an example to get a better sense of what I mean. The Pew Forum on Religion and Public Life has over time conducted surveys to assess American support for stem cell research. In 2002, 43% of Americans expressed support for stem cell research. Later in 2009, 58% supported this research. Can we conclude that support has changed in the population of all Americans? In other words, on the basis of this, can we conclude that support has gone up? Or could this difference just be due to chance variation during the sampling procedure? In other words, do we happen to just draw more people who support stem cell research in 2009 by chance? Notice this problem involves two populations. It might not seem like it does, but it actually does. So the first population is all Americans in 2009. The second population is all Americans in 2002. Now in stats, we're going to consider these two different populations because it's, not only might they consist of some people that are different, but maybe people have changed their minds. So we have two different populations. Two statistics were found as well by polling people in each of these populations. So the first statistic we found was P1 hat equals 0.58. That's a population that supported stem cell research in 2009. And then population 2, or P2 hat, is the population who supported stem cell research in 2002. Notice that I've switched the order of these two from over here, so, oh no I didn't, never mind. Okay, so we're good. Now P1, or the true population proportion of Americans who supported stem cell research in 2009, we actually don't know what that is. And P2, the one without the hat, we actually don't know what that is either. So the true actual proportion of Americans, if you looked at like every single person that supported stem cell research in 2002, we don't know that either. Now that's sort of unfortunate because if we knew what P1 and P2 were, then we would know for sure whether or not the rate at which people supported stem cell research increased. Unfortunately, we've only taken a smaller sample of people and found these numbers based on that, and so we aren't really certain that stem cell research support of it has gone up. Now, if we want to make some sort of deduction about how likely it is that it went up, we need to change all these ingredients to our hypothesis testing, and the second thing, or the first thing that we're going to change is the hypotheses. So we now have two populations to consider, and we need notation to start out our hypothesis test and come up with hypotheses. We're letting P1 represent the proportion of Americans who supported stem cell research in 2009, and we're going to have P2 represent the proportion who supported it in 2002. Now, the null hypothesis, we'll think about what that is first. Remember from previous sections in Chapter 8, the conservative status quo not worth a headline hypothesis, that's our null hypothesis. And in this scenario, it's that the proportions are the same, that the rate at which people supported, or the proportion that people at which people supported stem cell research, it's gone up. Or sorry, it stayed the same. Now, no change in support. How do we write that? What we do is we write H naught like this, and then our colon P1 equals P2. And so this just means that the proportion of Americans who supported stem cell research was the same in 2009 as it was in 2002. They were equal to each other. Now the alternative hypothesis is that these numbers are not equal to each other. So the proportion of Americans who support stem cell research has changed. They're not equal anymore. Now, we could have changed this to be a greater than symbol or less than symbol if we felt as if the proportion has gone up or gone down. If that was all our alternative hypothesis, that would have also been like a valid alternative hypothesis. But the null hypothesis is always going to be like P1 equals P2, that the proportions are the same for this kind of testing. Okay, so just a quick summary of the different kinds of hypotheses that you can have when you do testing like this for two proportion hypothesis tests. So your null hypothesis is always going to be that P1 equals P2. So notice how all of these have P1 equals P2 here. That one's pretty easy because you always just can write H not P1 equals P2. And then for the alternative hypothesis, you have three things that can happen. P1 is not equal to P2, P1 is less than P2, and then P1 is greater than P2. Now, how do you decide which one to use? If you're a scientist, it's sort of just like up to you. It's whichever one you think is the scenario that's going on. But for the homework, you're going to have to read the wording of the description kind of carefully and then use whichever one makes sense. So watch out for keywords like has gone up, less than, stuff like that. Okay, so you can pause and take a look at this summary if you want. We call the first one two-sided, second one one-sided, and third one one-sided, except for this first one-sided is left and the second one-sided is right. Okay. Now, this one's kind of complicated. Another ingredient we want to change in our hypothesis testing is the test statistic. So this is going to be our test statistic right here. We essentially take the difference between our two statistics and then we subtract 0. Now, you can just get rid of that 0, but the idea is that we want to know what the difference between these two is. Minus, and then 0 is like P1 minus P2, which we assume, well, I wouldn't think of it that way. Anyway, and then so we take this formula, we divide by standard error. Now, all of these here, you're going to end up having to find them to do various calculations related to finding the test statistic. And I'll do an example in another video where we find it by hand, but I would suggest just using StatCrunch most of the time because it's easier. Okay, now what other ingredients do we need to change? The conditions. So we're still going to have 4 conditions, but there's going to be a little bit of variation from what we've seen before. So we still have the condition large samples, and we have a very specific way of defining a large sample, and that is through showing that n1 times p hat is bigger than or equal to 10, n1 times 1 minus p hat is bigger than or equal to 10. And so what is p hat here? You have to be very careful because p hat is actually the pooled sample proportion. So you go back here, it is this, it's given by this formula here. Right here. So it's actually, what is it? It's like if you assume that the two populations are one big giant group, so population 1 and population 2 are all grouped together, it's the number of people in all who have the same characteristics. So if we were doing the previous example, it would be like all the people who support stem cell research in 2002 and 2009. So you're dividing by population in 2002 and 2009, and then like all the people who support stem cell research. So essentially, we have to figure out how many people are expected to support stem cell research if we group all of them together and make sure it's bigger than or equal to 10, and how many people are expected to not support stem cell research and see that's bigger than or equal to 10. Now we do this for both population groups that we sample, so population 1 and population 2. So N1 is the number of people in sample 1 and N2 is the number of people in sample 2. Now condition 2 is random samples, so the samples are drawn randomly from the appropriate population. So in practice this condition is impossible to check really unless we're there when the data was collected, but for the purposes of your homework you just need to watch out for the words randomly drawn, or you'll basically be told that the people are randomly selected. If you're not told that, you should just assume it and then write down in your hypothesis testing, we have assumed that the populations were randomly drawn. Now, independent samples, the samples have to be independent of each other. So what does that mean? Well, as an example, this condition is violated if the same individuals are in both samples that we're comparing. So you don't want to have the same people in both groups because they're more likely to have the same opinion. Like if you think about the example that we are thinking about, if you have some people in 2002 who support stem cell research and some people in 2009 who support it, it is more likely that someone will just keep the same opinion. And so you want to have the groups be totally different. Now, condition 4 is independent within samples. So the observations within each sample must be independent of one another. So When you have one group, say all the people in 2002, you don't want people's opinions to influence each other within that group. Same thing with the people in 2009. Now, if all these conditions are met, then we can do our hypothesis testing and it's totally valid. So I didn't go through these in a lot of detail because we're going to do other videos in this section where we go through these in detail. So we'll calculate the test statistic, we're going to check the conditions, we're going to do a hypothesis test, but those are all in different videos. This is just sort of like a brief outline.